that you have to do is go ahead and write down these notes. These notes are in regards to trig, and I'll go ahead and explain some of the things that are important from these two steps, especially how we start the equation. After you write the title, skip a line, you're going to write something else. Because right now, currently the 0 and 2 pi are set up as set notation. That was helpful. It was useful because we use that in it was helpful and useful, especially when we talked about like increasing and decreasing functions. It was a sure way to write that the x will go to a certain value, like it will start at a certain value, and that our and that we would like normally domain is the biggest reason we use this. But in this case, we are going to use something that you're more familiar with, and just because since we're solving and working with these things, we're going to use something that you feel safe for using. So we're going to actually use interval notation. So that's the only thing I want to make sure that I write down that's not everything else. All right, lovely. Okay, now the two things that I wanted for you to add on to these notes is that it's good to know set notation, it's lovely, but actually you feel safer and you feel more comfortable working with interval notation, especially when it comes to solving. Interval notation just means this. Okay, I think we all understand the angles are from 0 to 2 pi, right? What this is saying is this. This is what you're more used to seeing, that in our angle is going to exist between 0 to 2 pi. So it's rewriting what you wrote, but it's in a format that is easier for you to, and you feel safer working with this format. The reason why I'm working with this format is because when we need to change things, it's easier for you to understand what is happening. Because see, this one has a lower bound and upper bound, with the understanding that the middle means my angle. So that's important. You know, like in this case, we could talk about any angle between 0 to 2 pi. At times, though, do y'all remember that when we graphed some of these trig functions, they would not be, like sometimes we made them bigger, we amplified them, or we, especially like the period, do you remember the period was not necessarily between 0 to 2 pi, sometimes it was up to 4 pi or 8 pi, things that were even higher than that. That's going to be present in some of these. So like this next part, you see where it says step 2? when we work with these, we're going to isolate the trigonometric function. Actually, this portion, step 1, is pretty easy. Step 2, if you have a multiple of theta, then you have to multiply theta. Let me give you an example of what they're trying to tell you. Supposing, okay, so we're going to start with the standard one. Actually, probably write this down. Start with the standard one. What they're saying is this. If, let's say, you have an n, well, actually, let me make it in red so you can tell the difference. Let's say you have n. N represents like a natural number, also a fraction. But let's say you have n times theta. So, example, 2 times theta. So like the n is 2. Think about it that way. What you're going to need to do in order to express how it gets affected is that you're going to have to multiply n throughout the equation to express your new function in terms of that multiple, that n. The reason why this is important is because it affects your upper and lower bound. For example, let's say I have that green one. You see how it says 2 theta on there? You know that each theta is it represents 0 to 2 pi, right? Okay. If I have 2, and that's 1 unit circle. So if I have 2 unit circles, how much value do I have to combine together? 4 pi, right? Because I'll be going 2 pi and then 2 pi again. That's what this would represent. If this n was 2, supposing, then I'll be multiplying this by 2, this by 2, and this by 2. Oops. Which will result in an answer saying that you go from 0, that 2 unit circles will go from 0 to 4 pi. And that would make sense to us, right? That's what step 2 is asking you to do. That when you see a number in front of the theta, we're now going to take that into account and affect our equation in the same method. The general is the one in red. The one on top is kind of like the general idea of it. The green is just an example, because this is going to come up. So we're going to go ahead and perform that again. All right, lovely. Okay, now let's go into steps 3 and 4. So one of the things that sometimes we have to do is that, do y'all remember that when we graph trig functions, that sometimes we had this phase shift, especially when you're using that OFFS acronym, that if there was something inside the parentheses of the trig function, at times we either had to add it or subtract it, and we had to, more of anything, our starting point changed. It was no longer 0. That's the same thing here. You notice how our default goes from 0 to 2 pi? While sometimes we're not always going to start at 0. It's going to have to get moved and changed, and that's what it's saying. And it's exactly this idea. So actually, when you finish, just right at the ending of step 3. Well, actually, I want you to add this. You could continue writing, but I want you to add this idea that off our default, which is this, sometimes we have to add a value or subtract it in order to accommodate this phase shift. Because that was present too. In some of our trig functions that we work with, one of the things that was important that would happen is that we have to take into account that we may not always start at 0. We had to start somewhere else. It's exactly this that causes us also to refer to our trig values on a unit circle. Because see, after step 4, it talks about finding radian values around the unit circle that equal that value. But notice how it just says lower end. It's very general because our lower end may be changed. And it might be somewhere different. We may not always start at 0. We may start somewhere else. So they just say start at your lower end and continue around the unit circle as many times in the unit until you hit your upper end. Same idea. If your lower end is affected, normally your upper end is too. So I can't just say, oh, start at 0 and end at 2 pi with everything, because that wouldn't be true. That would not be accurate for all of them. I have a lower end and upper end that I got to take into account. see if everybody's finished writing. Okay, good. Now there's two more steps. So after you find the values, now this is going to be interesting. It's going to be a little bit unique because before I was very direct, and what I mean by direct is that I would ask you for a value given an angle. Like I would tell you, tell me, let's get an easy one. Let's say cosine. If I ask you what is the cosine value at 2 pi, remember that's the x value at 0, you would tell me 1, right? I was very direct with it. But let me ask you this. Supposing that we went around the unit circle a couple of times, or let's talk about one of the other values. Actually, that wouldn't be, I don't think 2 pi would be that good. Let's use this one. Let's use pi over 6. Pi over 6, what was the cosine value for pi over 6? I think it was square root of 3 over 2, right? Okay. All right. Now, supposing that I ask you the other way around. If I ask you, how many times does the square root of 3 over 2 appear on the unit circle? Like how many, under what values does the cosine, the square root of 3 over 2 appear in the unit circle? It means that you will have to go back in the unit circle and look, and you're going to find out that you have more than one location. Because remember how we built these, yeah, because it circulates. Not only that, but because we built it off using the same triangles, just in different positions, means that it's going to happen more than one location. So this is what's going to occur. You're going to expect to get more than one value. So once you find them, you're going to set each value equal to what the parentheses following the trig function, including the theta. Some of these trig functions, you end at step 5, because if there's nothing around the theta, then you're done. Can you write it the way you see what I have written in black ink? That's how you normally write an answer, where you put theta and you put, like that one I have 4 different values, but the dots are representing the value. Sometimes, though, we're going to have where theta, there's things around theta, so it makes it necessary to move to step 6. And step 6 states that we have to solve for theta. After solving, there is something unique that happens. All the values fit inside 0 and 2 pi. Because once we solve for theta, that's what theta exists, between 0 and 2 pi. Yes. Yes. All right, lovely. Let's see, just about everybody's almost finished. Right. So we'll move into our first exciting example. Getting to the actual implementation of all these stuff that we're writing down and dealing with. All right, excellent. Is anybody still writing? And we're all done? Okay. let's move into our first example. We're going to solve this. Okay, so go ahead and start this. I'll write this down. And then after that, I know, right? Kind of said, hey, you're making me. It's and a couple of things. I'm going to want you to start it with the idea of what data represents first in mind. Now, this is lovely because if you notice, you see how theta in itself, it's by itself? If anytime it's by itself, it makes the problem a lot easier. And the reason why it becomes easier and quicker for you to do is because it goes back to the default. So step one in what we're doing is understanding that we're going to be working with the bounds that theta is going to go from 0 to 2 pi. So that is, and nothing else needs to be done. So that's good to know. It's good in the sense because when I look at the unit circle, I'm just going to be looking at the unit circle that you're accustomed to seeing. Okay. Now step two will be to solve. Now some of these will require for you to solve them, others won't, because this one is just because of the way it's formatted. Now I'm going to write something down that you feel safe working with. If I wrote this down, I know that you would know in a heartbeat how to solve for x. So it would tell me add 1 to both sides, right? Divide by 2 and then take the square root. That's the exact same thing you're going to do with the sine, 2 sine square theta minus 1. The same exact thing. You're going to do 2 sine square theta minus 1 equal to 0. So when we implement trig, all the exact same steps. First thing, we're going to add 1 to both sides. That cancels this out. We're going to be left with 2 sine squared theta is equal to 1. After that, we're going to divide by 2 to both sides. Yeah, so it's going to become sine squared theta equal to 1/2. And then after that, we're going to take the square root. Okay. Now remember, when we take the square root, we got to keep in mind the important fact that we had before, where when we had plus or minus. Okay, we got to keep that as well with this. We got to keep that plus in mind and present when we work with these. All right. This is lovely because it gets me to my next step. Now I'm going to separate the square root. So it's still plus or minus, but now I'm going to separate the numerator and denominator. So we're going to have the square root of 1 divided by the square root of 2. Now the lovely and important feature is that square root, to simplify this, square root of 1 is 1. So this is going to become plus or minus 1 over the square root of 2. Yeah, and then I know a lot of you are looking at it and just, ready to rationalize this. Y'all are set, and that's what we're going to need to do. We do need to rationalize. So we are going to multiply by the square root of 2 top and bottom. And that's going to leave in this result. So that means that sine theta is going to equal to plus or minus the square root of 2 over 2. And this may seem familiar because that shows up in the unit circle, doesn't it? Lovely. Okay, so this is what you do afterwards. We're going to go ahead and you pull up a unit circle. And we're going to see where all this happens. Okay, so I'm going to pull up my unit circle. Let me clear this and write down. Okay. Now remember, the value we're going to be looking for is positive minus square root of 2 over 2. The important thing to remember about sine is that, remember that sine is y? Okay, so we're going to look at all the y values and just pick out the ones that are winners. Like this is, no. Does everybody see that that's it? This is a winner. No. Here's another winner. No. Here's another winner. No. Does everybody see the other winner? No. So there's 4 values. There's 4 answers that this occurs at. So what we're going to do next is what you wrote down on step 5. And where you express, you can express the answers in form of a set notation with data. Which means is this. Your step 5 says to do this. Take data and express pi over 4. Was it 3 pi over 4? 5 pi over 4. And 7 pi over 4. And that's step 5. Now, this is going to be one of those problems in where this is your solution. You don't need to do step 6. Step 6 is only necessary if there was some kind of number around the theta, like a 2 or a number adding it or a number subtracting. If there was something else that was there, then we would need to do step 6. But since it's solved, step 6 is not required in this case. It's been done. Now, if you're ever in doubt if you have a right answer, it's easy to check it. If you take any of these datas and put it up in that sine theta, you're supposed to get either positive square root of 2 over 2 or negative. So if you ever, and you could take any of those values and identify that that's what's going to become. Okay, I don't know if anybody wants me to prove it to them, but I guarantee that all these values are right. Okay, let's pick one. Pi over 4, okay. So then you type sine pi over 4. When you look at your unit circle, positive square root of 2 over 2. Any of the values will work. And actually all of them, if you have them as a solution, should work and give you either positive or negative. Yes? Yeah, go ahead. All right, lovely. Okay, let's move into our next example. Now, this next example is exciting in the sense that we're actually being challenged to see what does a 2 theta do to it. This is actually the first time that we're going to do one that has a modified angle. So write this down. And let's actually write down what is it that, and let's explore the effects. Now, we always start with our default. Our default being that a regular theta is going to be just from 0 to 2 pi. This is when we have to start thinking that our theta that's right here in the middle needs to start matching what is here to realize what effects it's having. So in order to do that, I'm going to multiply by 2 throughout this equation. And this is one of those examples that you see how you have 1 theta up there, which is 2 pi? This is exactly going back to that if you have 2 thetas, then you're going to have 2 unit circles, meaning that you have 4 pi. 2 pi plus 2 pi. And it shows up because when we do the multiply by 2 to here, to here, and to here, yeah, our ending result is that our 2 theta expresses itself as going from 0 to 4 pi. This is when step 4 becomes very important. One of the things that we wrote down about step 4 is that we're going to examine our values that we need to solve. Now, does everybody look that tangent theta is already solved? There's nothing that is around it, as opposed to the other one, which means that you kind of skip over that step 1 in your notes. It's already solved. So one of the things you're going to do is this. You're going to just look for when is tangent theta equal to 0 in unit circle. So now at this step, I want you to identify all the values on the unit circle. So write this down so you could have notes to yourself saying that you can identify all the values in the unit circle. After you're done writing it down, I want you then to bring out your unit circle and identify there should be 5 values that you need to come up with that represent this. Okay, I'm going to call on somebody randomly to share the 5 values. So look at your unit circle and identify the 5 values. Now, if you're having a hard time, remember, you're using 2 unit circles. So you're going from 0 all the way to 4 pi. the exciting thing is, let me clear all these. Let me go back to 2 to 27. See if we get selected. Let's wait for it. Side. Let's go. 10. Which falls on, actually, Amanda.
What? Don't remember 26.
So you got to pass this on Jacob then? Jacob, are you ready to take on the responsibility?
I got one of them.
You got one of them? Okay. All right, now good. So which one did you got left?
Pi.
Yeah, that's true. Yeah, pi is one of the solutions. But remember, there's 4 others. And the reason why there's 4 others is because, remember, we're going to go from 0 to 4 pi, right? So now, do y'all agree with me that at 0, tangent value 0? Yes. So that means one of your solution is actually 0. And then we're going to write, and then when we travel this way, when you start looking at the unit circle, you identify pi, because there's another 0 here. And then you went all the way around. Then what you should have done is gone all the way around, and then seen that you hit 2 pi, and then 0 shows up again. So here's my third one. And then remember, you go again, because we're going twice around the unit circle, because we're hitting 4 pi. So when we hit back here, this now represents 3 pi. It's from 2 pi, another pi, that's 3 pi. So here's another one. And then, yeah, well, this is 4 so far. And then afterwards, we went again and hit 4 pi. So my last value was the 4 pi that's on here. Well, because remember, we're restricted from 0 to 4 pi. And that came from here. Remember, we started with our default, right? And then afterwards, we applied this 2, and which modified it from 0 to 4 pi. But that's a good question. That's how you know where to go. How far or how many times to go or where. Because sometimes, see, we went twice over. Sometimes we're going to be asked to go only part of it, the unit circle. Yeah, so we're gonna write down. So the next step is this. You write down. This is when you do step 5, actually. Step 5 is kind of like at this portion, and where you're going to go ahead and write down. Now, you got to write down 2 theta, though, because that's what we express our solutions in right now. Our expression of our solutions are in form of 2 theta, which is 0, pi, 2 pi, 3 pi, and 4 pi. This is how our solutions are expressed right now. And this one is going to require for us to do step 6. Now, if you remember, step 6 means that we have to isolate the theta. So we're going to do that. Now, that's done pretty easily, because all we need to do in this one is divide by 2. So that's going to be pretty easy. Hey, so let's go ahead and do that. Let's isolate the theta. Now that you wrote down the solutions, let's isolate. Which means that the way I'm going to do this is divided by 2. So if I divide this by 2, that gets divided by 2, this solution gets divided by 2, that solution gets divided by 2, and this solution gets divided by 2. I went ahead and divided all my solutions by 2. It's going to end up that my theta then is going to be now 0, pi over 2, pi, 3 over 2 pi, and 2 pi. And this is lovely because I have all my solutions expressed in theta. Notice the solutions are between 0 to 2 pi. Does everybody notice that? That's going to be true with all of them. They're always going to be between 0 to 2 pi, just like our default. The other thing you do, if you're ever in doubt, I could take any of those and prove it to you with a guarantee there it's going to be right by putting it back into the original equation. Does anybody need a proof? Anyone? Okay. So which one? Pi over 2. Okay. So remember that we're going to take tangent. Remember how it was 2 theta? We're going to substitute pi over 2 there and see if it equals 0. Now the 2's, they cancel out, right? So we're going to have tangent. The 2's cancel. Tangent of pi is 0 based off the unit circle. So any of those can be proven to be right. And that's how you tell if you have right solutions. Yes? Oh yeah, that one too.
Just do it.
Just do it? Okay. No, that's not a problem. Just let me erase some stuff here so I won't have to. Well, actually, Yeah. Now, 3 over 2 pi. So if you have tangent 2, and then you have 3 over 2 pi. Yeah, the 2's were cancel out again, but I'm going to end up with tangent of 3 pi because the 2's cancel out, and that's 0 also. When you go back and you look at your unit circle. Yeah, it checks. So, but if anything, if you're ever in doubt, you always could try them out and see if they do equal. All right, lovely. Hey, let's move forward to another example, which has us now explore a phase shift. This one's interesting because it's applying two things. First of all, does everybody see where it says theta divided by 2? So that's 1/2, right? Being that we're now gonna look only at half the unit circle. That's one of the things that first does to it. The divided by 2 means that instead of going at 2 pi, I'm only going to go to pi. But in addition, y'all see that pi divided by 3? That's like a phase shift. That's like, remember when we talked about starting points when we graph? We don't always start at 0. That's going to happen with this one because of the pi over 3. So let's go ahead and work with it and see what the full effect of that is. First of all, we're going to start with our default one. 0 less than or equal to theta less than or equal to 2 pi. Always start with this one. And the first thing we're going to do to it, we're going to apply that, I'm going to apply first the divided by 2 to it, okay? So I'm going to divide everything by 2 to make it look like that. When you divide everything by 2, it has the effect in where I'm going to go now from 0 less than or equal theta divided by 2 to pi. And we kind of knew that already because for us, if I took the unit circle and cut it in half, then I'm only left with pi. The other thing we're going to do, though, we're also going to implement that phase shift. Does everybody see the pi divided by 3? Okay, let's go ahead and implement that and see the effects. So that means you're going to add pi divided by 3, add pi divided by 3, and add pi divided by 3 here. Your goal when you work with these problems is always make sure your theta matches the parentheses you have on top inside your interval. That's your one of the methods you have, one of the goals you have. Now let's talk about the results of this. I'm going to have that over here on the left, this is going to be pi divided by 3 now. It's going to be my lower bound. So no longer am I starting at 0. I'm going to start at pi divided by 3. And I'm going to be working with the angles. And then over here on the right, well, I got two fractions. First I got 1/3 pi, and I need to add it with the pi, so I'm going to go ahead and change 1 to its multiple, which is 3 over 3. 1 is a multiple of 3 over 3, which is another way to also saying it's equal. This is going to result in an answer of 1 pi plus 3 pi is 4 pi over 3. So these are my two new bounds. And all the other examples we worked with, we've gone from 0 to 2 pi, and then we even passed it twice when we went 0 to 4 pi. I want you to see if you're able to now be able to draw this on your paper. Draw this on your paper to get an idea how this will look. I'm going to call on somebody randomly to share with me what they should look like. Yeah. Now, you probably have an understanding of it, but we're gonna need to get some help here. So let's go ahead and find out which of the two it is. All right, the exciting pick is on this one. Wait for it. All right, two. So Alex. Now, let's bring up the unit circle so we could share unit circle. Now, in this case, Alex, what were you able to share with me? It starts at pi over 3. Good. All right. So, actually, you know what? That's actually pretty good. This is what Alex is saying. It starts here. Okay. So, he says it ends here. And it's pretty much this. Oops. Let me I don't want to read. It's going to be this half of the unit circle, which means it's all these values over here. Oops. Does everybody see all the values I have encompassed in that circle? Those are exactly the values you're going to pay attention to. Nothing else. You see all those values on the right? You're not going to pay attention. Only these values right here, because we're only talking about half of the unit circle with the phase shift. That's exactly what happened. We took half the unit circle and we moved it. We rocked it, pi over 3. What I want you to do now is identify the value, this one. Let me have you write it down. I want you to identify the value where in the unit circle that it's been modified. This is step 4. Step 4 and 5. Where tangent theta equals 1. Because that's what we started with. If you're trying to figure out where 1 came from, it came from the very top of the problem. Identify that. I'm going to call on somebody randomly or what the answer should be. Right, good. Go ahead and see who may be ready to answer this. Okay, let's wait for it. Do it. All right, 13, which is it you, Dylan? All right, Dylan, what answers did you come up with?
3 pi over 4, 5 pi over 4.
Well, only one of those is right. Let me share with you why. You stated 3 pi over 4, right? But look at the tan. What tan values does that one have? You see how it's -1? -1 doesn't qualify because my answer is only +1. So the only solution there is this one right here. Y'all see the one there? So the only solution that exists that where tangents equal to 1 is only one value. This is the first time we had an experience with these, because so far I've written down like 4 more solutions. We only have one solution in this case, which means that this equation over here, when you do step 5, where you write it theta, you're going to write it down. Ooh, we're going to leave soon. Okay, you're not going to write it like this. You're going to write it as theta divided by 2 plus pi over 3 is equal to the said notation of, what was it, 5 pi divided by 4? Is that right? Yeah. Okay, good. Okay. This one will require for us to do step 6. Step 6 will be solving for theta. I'll deal with that since we're running out of time. We'll do that tomorrow. Step 6 on this, and then one other